Hi everyone, today we will discuss about another problem that can be solved efficiently with dynamic programming, just to illustrate a little bit how you can implement in practice and use an approach such as dynamic programming to solve different kind of discrete optimization problems. The problem is the following. So you are given a sequence of number denoted S1 until Sn, and these numbers are non-negative numbers. And then you are also given k, which is an integer, a positive integer. And the goal here will be to split the sequence into k subsequences so that the maximum sum of consecutive elements in any of the subsequence is minimized. So let's take one example here. We have this sequence of numbers, k equal to 3. I will split it in 3, for instance, like this. And what you can see is that the sum of this one, okay, the sum is 17. And so this one is the maximum, right? Because here you've got 13, and here you've got 9, 10, and you've got, if I'm not mistaken, 15, right? And so the goal is to minimize the maximum, which is here 17. Okay, you want to find the optimal split of the sequence to minimize the maximum sum inside any of the subsequence. Okay, just to make sure that everybody get it right, this is another example, so another sequence a little bit larger, and you are given k equal to 4. So put the video on pause and try to solve it, and then I will explain to you what is the optimal solution here. Okay, the optimal solution is 13 here. And you can get it by splitting it like this. Yeah, this is 1. Then you've got, this is already 13, so this is 1. Okay, you've got 13 here. 13 here. Here you've got 10. 13. And then you've got this one, which is 9. Okay? You cannot find any better division of this sequence into a partition of 4 subsequences. Okay, how to solve this problem in dynamic programming? First, I will explain what are the typical errors that students do at the exam when I ask such a question. Okay, so the typical question that I ask at the exam is, can you formulate this problem as a dynamic programming? And I write explicitly that you should write the recurrence equations. And don't forget the base case. Then as the next question, I ask, can you sketch the code to solve it? For instance, in Java or Python, inside one of your favorite language. Then I generally ask, what is the time complexity to solve this problem, and can you justify it? And then finally, I give you a small instance of the problem, and I ask you to illustrate the execution of your dynamic program on this small instance. Okay. Typical errors is this one for the first question is, can you formulate this problem as a dynamic program? Usually students give a recurrence equation, but I cannot understand it. I cannot understand it, and usually I cannot understand it because the range of parameters are not specified. And also it's not explained what they do represent, these parameters. Okay, just to show you an example of something that I cannot understand is this one. Okay, one student could write me for this problem a solution like this one. Okay, the problem is, what does this represent? You should write in natural language what OIL represent. What is I, what is L? Okay, I don't know, I cannot guess it. And then you've got the maximization over J, but the range of J is not given here. I don't know what is the scope of J. Is it starting from 1? Is it going up to n and the size of the sequence? Is it going up to k? I don't know. It's not written. Okay? And so again, what does O represent? And also there is no base case. So you give me a recurrence equation, but this recurrence equation will not stop. Okay? And so it's possible that at some point the parameters will go negative. Is it allowed? Is it not allowed? Usually, you always have a base case if you write a recurrence equation, just to make sure that it will eventually stop. Okay? So, multiple choice question to start a little bit thinking about this problem. let's assume that OIL, okay, with I from 1 to n is the size of the sequence, okay? If you remember, the sequence was S1 up to Sn, okay? And L can range from 2 to k, because if there is only one partition, it's quite obvious what you should do is take all the sequence, right? You cannot do anything else. So if k is equal, if the length, the number of partitions is equal to 1, it's quite obvious you take everything. So this is the recurrence case, and this denotes the optimal solution to the problem on the prefix subsequence from S1 to Si. Okay, this is quite this is used a lot in dynamic programming, and this is also the approach that we have chosen for the knapsack. If you remember, we were also limiting the items from 1 up to item I. Okay, that's also the case here. And we will also limit here, with one additional parameter, we will also limit the number of partitions. Okay, it can be at most L partitions here. Okay, or exactly L partition. And then what is the optimal value for OIL if I'm allowed to reuse the previous computation that I have? Okay, so you have these three possibilities, and I ask you what is the correct one. Okay, think about it a little bit, put the video on pause again, and then you can start it again. I will explain to you the solution and why you can immediately discard some of these possibilities. So the first possibility here, you will take the maximum here between OI minus 1L and OI minus 1 L minus 1 and then plus SI. Okay, it's already quite strange, right? Because you want to minimize something, and here you take the maximum of the two, and there is no minimization in it. So it's quite clear that this will not work, right? Okay. And also, why would you take only I minus 1 and just add this one? So it means that you probably just are creating a split just at the end of the subsequence up to Si, and you will isolate Si in it. So probably it's not working, okay? So clearly this one is not good. Okay. Then for the same reason here, you are isolating the last one as a subsequence. There is no reason of doing that, okay? So you can discard that one as well. The next one, you will try to split here. You see that there is a split point J, okay, and you will try to find a split, and you will start counting from that point. You will create a subpartition from G plus 1 up to Si. Yes, that could work. Then you will take the minimum with OJ L minus 1. Let's see how it's different from the 0.4 and the 0.5. Okay. You want to take the maximum of the minimum. Oh, this looks a little bit strange, right? I think it should be the opposite. Okay. You want to take the minimum of the maximum sequence according to the statement of the problem. Okay. So this is not good, right? This is why it's not correct. So this one is fixing that problem. You take the minimum of the maximum subsequence. Okay, the bottleneck is the subsequence with the largest sum. Okay, so here you just have created a split point. Sorry, come back. Here you have created a split point of this subsequence, right? And then you have the optimal subsequence. You take the maximum of the two, right? And you want to minimize that. So this one is a correct one. Okay. And then the previous one, what's the difference with the previous one? You see here that, ooh, sorry. I made a mistake. The correct one, sorry. The correct one is this one, and this one is also not good, okay? Why? The difference here is that you are starting from Si here, but it's not correct because you want to try to find the splitting point, which is J. Okay, and so you will start counting from J, okay? And you will start additioning from J and not from Si. So this is the proposition number 4 that is correct. The number 5 is not correct from that perspective because it's starting the summation from si plus 1. But I is precisely the limit here. Okay, you can only use the element from 1 to I. So it doesn't make sense at all to start to make the summation from I plus 1. Okay, let's try to get a little bit to get a better understanding of this recurrence equation that I just have presented here. Okay, so basically what you are doing in this recurrence equation is that you are creating a splitting point here. You are creating a splitting point. Okay, this is OJL minus 1. Okay, and you create a split point at J, and then you will take the summation of the last part here. Okay, then you will take the maximum of the two here, and this is what you have here. You create a split point starting from J, so you create a new subsequence here. Of course, you are allowed to use, sorry, I will remove myself from here. You are allowed to use 1 minus L minus 1 subsequence here, okay? Because the limit of the recurrence is L, so here you are allowed to use L minus 1 because you already have created one here. Okay, you take the maximum of the two, and of course you need to take the maximum over all the possible splitting points. You take the minimum over all the splitting point J. Okay, so this is what you do. And the best case, the best case usually is for parameters with equal to 1, for instance. It's also the case here. So the best case is with only one partition, right? So if you have only one partition, okay, this is L. If you're allowed to use only one partition, then it's quite trivial. You only can take all the elements from the subsequent S1 to Si. You just make the summation of all of them. Okay? And there is also the one with the sequence of length L, or of length 1. If you have a sequence of length 1, whatever the number of partition, okay, you can only take this only single element, which is restricted here by I equal to 1 in the recurrence. So this is the base case. And also you should not forget in your answer at the exam to characterize what is the optimal solution, because you have written the recurrence equation, but then you need also to explain what is the optimal solution. For what parameters do you obtain the optimal solution? And of course here is for O and K, and in the size of the initial subsequence, and K is the maximum parameter, the maximum number of splits in the sequence. Okay. So let's see in practice how the computation works. So I have already initialized here, you see my table here, my table of the states that I have computed with the base case. So these are the base case, okay? If the subsequence, if the limit is equal to 1, you can just take the summation, okay? So for instance, here, k equal 1, you can go up to that limit, okay? This is the parameter I, limit 3, so you just take the summation, 3 plus 2 plus 1, okay? This is mean this subsequence, so this is 6, okay? 3, it's because 2 plus 1, 10 is equal to 4 plus 3 plus 2 plus 1, and so on, okay? So you've got the base case here. And then we are interested to compute this entry, okay? We are interested to compute this entry. To compute this entry, I will, so this is 052. I will take the minimum and I will consider all the previous splits, okay? I will consider the split with just one subsequence at the end, which is this one, then the 2 last ones, and then the 3 last one, and then the 4 last one, okay? And then I take recursively the optimal of the previous subsequence. So in this case, I will take the minimum of the maximum between 10 and 5, okay? So, yes. And then I also need to take, so the maximum between 10 and 5 is this one, okay? So you create a partition with 5 as the last element, so you've got 5 here, okay? And then the previous one is this one. If you can go up to that limit, okay, with k equal to 1, you take this one. And so you will take the maximum between 5 and 10, and this will be your objective function on this subsequence, which will be 10, right? Then you consider the last two ones as a subsequence. Okay, so you've got 4 plus 5, which is the value of the last subsequence. And then what you get before was 6, so you find it here. Then you take the last three ones, 3 plus 4 plus 5. Okay, this would correspond to this one, and take the previous one, 3, take the maximum of the two elements, and then you have got this one as the last subsequence, so 2 plus 3 plus 4 plus 5, and the maximum is 1, which is this one. And you take the minimum of all this one, which is the optimal splitting point on this subsequence. Okay, and you get 9 as a result, and so you will simply write 9 here as the next entry. Okay, and you will fill in the table like this. Okay, this line first, and then this line, and so on, and you will fill in the table. Okay, and this corresponds exactly to what we have written in the recurrence equation. What is the time complexity for computing this? The time complexity for computing this is, of course, at least the size of the table, right? This parameter will range from 1 to n, and this parameter will range from 1 to k. So the time complexity will at least be n times k, right? This is pretty clear, but then I also need to add or multiply the complexity to compute the recurrence equation, right? So I have a minimum over the range here of j from 1 to 1 up to I minus 1. So again, I need to multiply it by n because of this. Okay, and then we also have to take into account how to compute this. Taking the maximum between two elements is order of 1, but doing the summation of this prefix can also take n. So again, I need to multiply by n here, okay? So it means k times n cubed. Okay, this is my time complexity, order of k times n cubed. Can we go a little bit faster? The answer is yes, we can go a little bit faster, because computing this subsum could be done in order of 1 constant time. Granted, I have already pre-computed some values, okay? So assume my sequence is this. And I want to retrieve the subsum of this one, okay? What I can do is pre-compute what I will call the prefix sum. I will call the prefix sum. And this will be 2, and then 2 plus 3, 5. 5 plus 1, 6. 6 plus 4, 10. 10 plus 5, 15. 15 plus 6, 21. And then 28. Okay? If I'm interested to compute this, I can simply take the prefix sum. So I can simply do 15 minus 2. Okay? Up. And you've got the prefix sum, which is 13. Okay, so if you do that, you can compute this in order of 1, which means that this last n that I have added in my naive implementation will be 1, and so you will lower the time complexity to kn squared instead, which is much better already, right? So this is always nice to think about pre-computation, because if you do some pre-computation like here, the prefix sum, sometimes you can lower a little bit the time complexity in your dynamic program implementation. In the next video, I will of course explain how to implement this using also the prefix sum computation in Java, and the source code will be available at this address.